Welcome to Ultimate Sleep Doctor. Tonight, we'll journey back in time, not to chase excitement, but to discover quiet wonder. For millions of years, colossal creatures roamed our planet, dinosaurs. These ancient beings, built on incredible scientific principles, held secrets within their bones and footprints. Their existence reminds us of the Earth's vast and ever-changing story, a narrative of immense scale and patient evolution. It's a beautiful reminder that even the most powerful forces have a natural rhythm. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. The story of dinosaurs isn't a sudden explosion onto a suddenly empty planet. It's a story of incredibly slow, patient change, a remarkable journey that stretched back hundreds of millions of years. To truly understand where dinosaurs came from, we need to travel back to a time when the Earth looked very different, a time when giant reptiles ruled the land and the skies. Our journey begins with a group of animals called archosaurs, and understanding the archosaur lineage is absolutely key to unlocking the secrets of dinosaurs. Archosaurs, meaning ruling reptiles, were a diverse group of reptiles that thrived during the Triassic period, which began around 252 million years ago. They weren't dinosaurs, not yet, but they were the ancestors, the stepping stones, leading directly to the incredible creatures we know and admire, the Triceratops, the Tyrannosaurus rex, and the Velociraptor. Initially, archosaurs included a fascinating mix of forms. Some were small, bipedal predators like Erythrosaurus, a little dinosaur-like creature with short limbs and a sharp beak, while others were enormous, quadrupedal herbivores like Plateosaurus, which resembled a giant crocodile with a long neck. These early archosaurs occupied a wide range of ecological niches, showcasing a remarkable adaptability. The defining characteristic of the Archosauriforms, the group that contained all the ancestors of dinosaurs, was a particular arrangement of their limbs. Notice how many of the early archosaurs walked on two legs, a posture we see so prominently in dinosaurs. This bipedalism, or walking on two legs, was a crucial evolutionary development. It's not that they started walking upright. Rather, the genetic changes that allowed for a more efficient, balanced gait began to appear within the archosaur lineage. These changes involved modifications to the bones of their legs, allowing for a stronger, more direct push-off during movement. This leg structure was already present in some smaller archosaur groups, like the early phytosaurs, modern reptiles that resemble crocodiles but live in freshwater, offering a clear evolutionary link. But bipedalism alone doesn't make a dinosaur. The archosaurs were experimenting with different body plans, and the key to the dinosaurian transition lay in several interconnected developments. One critical area was the skeletal structure of the hip. Dinosaur hips are uniquely shaped, with a broad, bowl-shaped acetabulum, the socket where the leg bone fits, providing a much larger surface area for the femur, the thigh bone, to attach. This allowed for greater muscle attachment and significantly more powerful leg movements. The early archosaurs had relatively small acetabula, resulting in less powerful leg muscles. Over millions of years, the archosaur lineage gradually increased the size and complexity of this joint, building the foundation for the incredible power and speed that would eventually characterize dinosaurs. Another crucial change involved the evolution of the wrist. Dinosaur wrists are incredibly flexible, allowing for a wide range of motion. This is due to the expansion of the carpal bones, the small bones in the wrist. These expanded wrist bones provided greater mobility, which was essential for a more agile and coordinated movement, particularly important for hunting or escaping predators. Again, this development was a gradual process within the archosaur family, with the earliest examples appearing in groups like the early ornithopods, the group that included the famous Stegosaurus and Iguanodon. Furthermore, the archosaurs began to show signs of developing a more upright posture. The vertebral column, the backbone, began to curve more significantly, allowing the body to be held higher off the ground. This shift in posture was coupled with changes in the ribcage, creating a more streamlined body shape that reduced drag and increased efficiency. These changes weren't drastic overnight, but rather a series of incremental adjustments that occurred over countless generations. It's important to remember that evolution doesn't happen in leaps and bounds. It's a slow, continuous process of adaptation. The transition was also influenced by changes in diet. As the archosaurs evolved, some began to specialize in herbivory, eating plants, requiring stronger jaws and teeth for grinding tough vegetation. This dietary shift likely drove further evolutionary changes in the skull and jaw musculature. The development of dental batteries, rows of tightly packed teeth that wore down as they were used, is a prime example of this adaptation. These changes ultimately paved the way for the diverse feeding strategies seen among the early dinosaurs, allowing them to exploit a wider range of resources. It's thought that the first true dinosaurs emerged sometime during the late Triassic period, likely from within the ornithopod archosaur lineage. These early dinosaurs, such as Herrerasaurus and Aeoraptor, already possessed many of the defining characteristics of dinosaurs: bipedalism, an upright posture, a flexible wrist, and a robust skeletal structure. However, they still retained some archosaur features, like a longer tail and a less specialized skull. The story of the early dinosaurs isn't just about a single, transformative event. It's a story of a gradual accumulation of changes, a complex interplay of genetic mutations, environmental pressures, and adaptations to different lifestyles. The archosaurs provided the raw materials, the foundational building blocks, upon which the incredible diversity and success of the dinosaurs were ultimately built. It's a humbling reminder of the power of evolution and the extraordinary journey that led to the rise of these magnificent creatures. A journey that began long ago with a group of reptiles called archosaurs. Understanding this lineage allows us to truly appreciate the incredible evolutionary history behind every footprint, every fossil, and every magnificent dinosaur skeleton we study. The question of what dinosaurs looked like has fascinated scientists and dreamers alike for over a century. Early reconstructions often presented dinosaurs as scaly, reptilian behemoths, a reflection of their closest living relatives, the crocodilians. However, our understanding of dinosaur skin has undergone a dramatic shift, largely thanks to the remarkable discoveries of fossilized feathers and intricate skin impressions. The fossil record, once a frustratingly sparse collection of bones, is now yielding increasingly detailed glimpses into the true appearance of these magnificent creatures. It's a story of constant refinement, of revising our initial assumptions based on new evidence. Initially, the overwhelming evidence pointed towards dinosaurs being largely covered in scales, much like modern reptiles. Fossilized skin impressions, particularly those found in the dinosaur fossil beds of China, provided strong support for this idea. These impressions weren't just simple, uniform scales. They revealed complex patterns, including interlocking scales, overlapping plates, and even small, brush-like structures. The discovery of Eudyrannus, a tyrannosaur relative, with exquisitely preserved feathers, initially thought to be simple filaments, showed that at least some dinosaurs had developed this integumentary feature. This discovery challenged the long-held notion that feathers were exclusively associated with smaller, bird-like dinosaurs. The fossilization process itself plays a crucial role here. The conditions necessary for feathers to be preserved are relatively rare. They require specific mineral conditions, often in fine-grained sediments like volcanic ash, which act like a preserving agent, trapping and mineralizing the delicate structures. The debate surrounding dinosaur skin, particularly concerning the larger theropods, the meat-eating dinosaurs like Tyrannosaurus rex, continued for many years. The sheer size of these animals made it difficult to envision them covered in feathers. How could a creature the size of a school bus be effectively insulated with plumes? However, growing evidence suggests that the situation was more nuanced. While large theropods likely possessed fewer, larger feathers, perhaps concentrated along the back, arms, and tail, it's increasingly accepted that they weren't entirely bare. The fossil record reveals microfeathers, tiny filaments that would have provided insulation and possibly assisted in display. These tiny structures, often found embedded in the teeth of predators, suggest that even the most fearsome carnivores were adorned with some form of plumage. Furthermore, the discovery of fossilized skin impressions displaying vascular patterns, a network of blood vessels beneath the skin, suggests that the integumentary system, including the circulatory system, was far more complex than previously imagined. Beyond feathers, researchers have identified numerous other integumentary structures through fossil evidence. The Steinbeißia fossil, for instance, a small ornithomimid dinosaur, ostrich-like dinosaur, provided the first direct evidence of a dinosaur having a protoburlap, or protoindumentum, a loose, collagen-based covering beneath its skin. This indicates that many dinosaurs, particularly smaller ones, possessed a layer of insulating tissue, similar to that found in modern birds and mammals. This layer would have significantly improved their ability to maintain a stable body temperature, a crucial adaptation for surviving in diverse climates. The study of dinosaur skin isn't just about aesthetics. It offers profound insights into dinosaur physiology and behavior. The presence of feathers, for example, likely played a role in thermoregulation, providing insulation against the cold, but they likely served a wider range of functions. Feathers could have been used for display, attracting mates or intimidating rivals. They could have been employed in gliding or even powered flight, particularly in smaller, more agile dinosaurs. The patterns and colors of feathers, revealed through pigment analysis of fossilized feather impressions, further complicate the picture. Some dinosaurs likely boasted vibrant, iridescent plumage, while others may have been camouflaged to blend into their surroundings. The discovery of fossilized skin glands, structures that produced oils or mucus, is also shedding light on dinosaur skin care. These glands could have been used to lubricate the skin, protect it from the sun, or even to secrete defensive chemicals. The study of these secretions, through the analysis of fossilized resin and other organic materials, provides a window into the grooming habits and self-defense strategies of these ancient animals. Furthermore, advanced imaging techniques, such as synchrotron microcomputed tomography (micro-CT), are allowing scientists to virtually peel back the layers of a fossilized skin impression, creating 3D reconstructions of the integumentary structures in unprecedented detail. This technology is revealing the intricate architecture of dinosaur skin, the arrangement of scales, feathers, and glands, and even the presence of subcutaneous fat, a crucial energy reserve for these large animals. The ongoing research on dinosaur skin highlights the dynamic nature of scientific understanding. What was once considered a fringe theory, that dinosaurs were covered in feathers, has become a cornerstone of our knowledge. The fossil record continues to surprise and challenge us, and we can anticipate even more groundbreaking discoveries in the years to come. It's a testament to the power of observation, meticulous analysis, and the unwavering human desire to understand the lost world of the dinosaurs. Ultimately, reconstructing the appearance of dinosaurs is a collaborative effort, combining paleontology, biology, chemistry, and imaging technology. It's a reminder that the past is not fixed, but is constantly being rewritten as we gather new evidence and refine our interpretations. So, the next time you see a bird soaring through the sky, remember that it's not just a modern descendant of a long-extinct lineage. It's a living link to a world where dinosaurs once ruled the earth, and their skin, scales, feathers, and all told a story of incredible adaptation and evolution. The world of dinosaurs wasn't just shades of brown and gray, as many people might assume. Scientists are increasingly uncovering evidence that suggests a vibrant, colorful past for these magnificent creatures. It all hinges on a remarkably resilient chemical, melanin, and the way it's preserved within fossilized remains. Melanin, the same pigment that gives humans our skin and hair its color, is surprisingly stable over millions of years, and when found in dinosaur fossils, it offers a powerful tool for reconstructing their coloration. Initially, the idea of brightly colored dinosaurs seemed almost unbelievable. The prevailing view, based on the lack of preserved soft tissues and the typical weathering processes that affect fossil bones, led to a monochrome interpretation. However, advancements in analytical techniques have dramatically shifted this perspective. Researchers began to realize that even trace amounts of melanin, concentrated in specific locations like bone surfaces, feathers, or even skin impressions, could hold vital clues. The process begins with a technique called pyroglyph analysis. This involves carefully scraping away layers of surface dirt and weathering from a fossil's exposed bone surfaces. This is a painstaking process, often undertaken under microscopes, and requires an incredibly delicate touch. The goal is to reveal any microscopic traces of melanin. Melanin itself isn't immediately visible. It's dark brown or black, and it blends seamlessly with the surrounding fossil material. Once the surface is cleaned, scientists employ techniques like reflectance infrared spectroscopy, RIRS, and Raman spectroscopy. RIRS works by shining infrared light onto the fossil surface and analyzing the wavelengths of light that are reflected back. Different pigments absorb and reflect infrared light in unique ways, allowing scientists to identify the presence and type of melanin. Raman spectroscopy uses a laser to excite molecules within the fossil, causing them to emit light. The pattern of this emitted light creates a unique fingerprint that can identify the pigment's chemical composition. These spectroscopic analyses aren't just identifying that there's melanin present, they're revealing the specific types of melanin. There are several forms of melanin: eumelanin, which produces brown and black pigments, and pheomelanin, which generates red and yellow hues. The ratio of these two types of melanin is key to understanding a dinosaur's color. For example, a higher proportion of eumelanin would suggest a darker, blacker animal, while a greater amount of pheomelanin would indicate a reddish or yellowish coloration. The most exciting discoveries have come from examining fossilized feathers. Many theropod dinosaurs, like Velociraptor and Deinonychus, are now known to have had feathers, but the color of these feathers has been a mystery until recently. Analyses of fossilized feathers from specimens like Anchiornis huxleyi have yielded astonishing results. Researchers have identified significant amounts of pheomelanin within the feathers, suggesting that these dinosaurs weren't drab, brown birds, but rather sported vibrant reddish-brown, yellow, and even orange plumage. Furthermore, the concentration of melanin within the feathers is linked to their function. It's hypothesized that brightly colored feathers played a role in display, used for attracting mates or intimidating rivals. The sheer intensity of color suggests a significant investment in visual signaling. Beyond feathers, researchers are also investigating melanin deposits in fossilized skin impressions. These impressions, often found in fine-grained sedimentary rocks, can sometimes retain traces of pigment. While the preservation quality is typically lower than with feathers, recent studies have identified traces of melanin in skin impressions from various dinosaur groups. The techniques are expanding to include analyzing the color of fossilized teeth. Melanin can be incorporated into enamel during tooth formation. An analysis of fossilized teeth has provided surprising insights into the coloration of carnivorous dinosaurs. Some studies have suggested that Tyrannosaurus rex, for instance, may have had darker teeth than previously thought, possibly contributing to its intimidating appearance. It's important to note that reconstructing a dinosaur's exact coloration is a complex process. The preservation of melanin isn't always perfect, and contamination from the surrounding environment can influence the results. Scientists employ rigorous protocols to minimize these issues, including careful sample selection, control experiments, and statistical analysis. The study of dinosaur coloration is still relatively new, and we're only beginning to scratch the surface of this fascinating field. As analytical techniques continue to improve, and as more fossil specimens are examined, our understanding of the visual world of dinosaurs will undoubtedly become even richer and more detailed. It's a journey into a lost world of color, revealing that dinosaurs were perhaps far more visually striking than we ever imagined. Future research promises to not only paint a more accurate picture of dinosaur appearance, but also to shed light on their behavior, ecology, and evolutionary adaptations. Dinosaurs weren't just enormous reptiles. They were complex creatures grappling with fundamental challenges of survival, and one of the biggest was keeping warm. Scientists have long wondered how dinosaurs managed to thrive in a world where temperatures could fluctuate dramatically, sometimes scorching hot, sometimes bitterly cold. It's a puzzle that's led to fascinating debates and sophisticated modeling, and the core of the discussion revolves around how they regulated their body temperature. The simple answer, that dinosaurs were like modern-day birds, is complicated, and the current understanding points to a nuanced strategy, often described as mesondothermy. The earliest ideas about dinosaur thermoregulation often leaned toward endothermy, a system where dinosaurs possessed a consistently high body temperature, much like a mammal or bird today. Endotherms generate most of their heat internally through metabolic processes, relying on shivering or sweating to dissipate excess heat. The sheer size of many dinosaurs, think of the immense Argentinosaurus or the powerful Tyrannosaurus rex, would have presented a significant challenge for maintaining a high, constant temperature through internal heat alone. The energy required to sustain that level of heat, particularly in a large animal, would have been enormous, demanding a continuous and substantial food intake. This conflicted with the fossil record, which demonstrates periods of environmental change and fluctuating food availability. However, purely relying on endothermy didn't quite fit the evidence. Instead, scientists began to propose mesondothermy, a middle ground. Mesondothermy suggests that dinosaurs weren't consistently warm like mammals, but they weren't simply cold-blooded reptiles either. Instead, they likely possessed a fluctuating body temperature, with a core temperature that was higher than that of modern reptiles but not as consistently high as that of true endotherms. This system would have involved periods of intense activity, like a chase or a territorial display, where they would boost their internal heat production. During these times, they might have exhibited behaviors we now associate with true endotherms, such as panting or perhaps even limited shivering, to maintain that elevated temperature. The key evidence supporting mesondothermy comes from several sources. Firstly, the presence of feathers, especially in smaller theropods like Velociraptor, is crucial. While feathers initially evolved for insulation, research indicates that they also played a role in thermoregulation. The ability to fluff feathers around the body would have created an insulating layer, trapping a layer of warm air and minimizing heat loss. Furthermore, recent studies of feather microstructure reveal a complex arrangement of barbs and barbules, incredibly similar to that found in modern birds, suggesting an evolutionary link directly related to thermal control. Secondly, the fossil record shows that many dinosaurs were active during cooler periods. The discovery of dinosaur footprints in areas with ice or snow, combined with bone histology, the study of microscopic bone structures, reveals signs of increased metabolic activity during colder seasons. Bone histology reveals higher rates of blood flow and cellular activity in dinosaur bones from colder periods, indicating that they were working harder to maintain their core temperature. This contradicts the idea of a reptile-like state of inactivity during the cold. The degree to which dinosaurs employed mesondothermy probably varied significantly depending on their size, species, and the surrounding environment. Smaller theropods, like Velociraptor or Deinonychus, would have been better equipped to regulate their temperature because they had a higher surface area to volume ratio. This means they lost heat more quickly, requiring them to actively expend energy to maintain their core temperature. Larger dinosaurs, such as the armored Stegosaurus, likely relied more heavily on insulation through feathering and potentially thick skin, and perhaps spent more time in sheltered environments to minimize heat loss. Furthermore, scientists have used sophisticated computer modeling to simulate dinosaur thermoregulation. These models demonstrate that mesondothermy is a plausible strategy, particularly for dinosaurs with feathers. These simulations show that feathered dinosaurs could have achieved an internal temperature higher than that of reptiles while still conserving energy compared to a fully endothermic system. The models account for factors such as ambient temperature, activity level, and the insulating properties of feathers. The debate isn't entirely settled, and ongoing research continues to refine our understanding. Some scientists believe that certain dinosaur groups may have exhibited a more hyperendothermic strategy, a system closer to true endothermy, particularly during bursts of activity. However, the prevailing evidence strongly supports mesondothermy as a fundamental mechanism for dinosaur thermoregulation. It's a remarkable adaptation that allowed these giant creatures to flourish in a diverse range of climates, a testament to the ingenuity of evolution. Ultimately, the story of dinosaur thermoregulation highlights the complexity of these extinct animals. They weren't just majestic predators or lumbering herbivores. They were active, intelligent creatures constantly adapting to their environment. By understanding how they regulated their body temperature, we gain a deeper appreciation for the challenges and triumphs of dinosaur life, adding another fascinating layer to our knowledge of these incredible beasts. The world of dinosaurs wasn't just about enormous size and fearsome teeth. It was also a world of astonishingly intricate and rapid growth. Paleontologists have developed increasingly sophisticated methods for studying how dinosaurs actually grew, and it's revealing a much more dynamic and surprising story than we once imagined. Instead of simply guessing based on the overall size of a fossil, scientists are now examining the patterns etched within dinosaur bones themselves, tiny, beautiful records of development. The key to this investigation lies in something called growth lines, or incremental markings. These aren't like the rings you see on a tree trunk, though they serve a similar purpose. Every time a dinosaur bone grows, it adds a new layer of tissue, and this growth isn't always smooth. Instead, it often leaves behind a subtle, wavy line, a ridge, or a series of small bumps on the bone's surface. These markings represent periods of rapid growth, and the spacing and density of these lines provide a chronological record of the dinosaur's life. Initially, researchers relied on simple measurements, the length of growth lines, to estimate growth rates. But this was often hampered by the fact that growth lines can be distorted or obscured by weathering and damage over millions of years. More recently, advancements in imaging techniques have revolutionized the field. Computed tomography, or CT scanning, allows scientists to create detailed 3D reconstructions of bones without damaging them. These scans reveal incredibly high-resolution images of the growth lines, showing not just their length, but also their shape, orientation, and the spacing between them. The analysis of these growth lines doesn't just give us a rough estimate of size. It tells us how a dinosaur was growing. Some dinosaurs, like the enormous sauropods, the long-necked giants like Brachiosaurus and Argentinosaurus, exhibited periods of exceptionally rapid growth, especially during their teenage years. CT scans of juvenile sauropod bones show incredibly dense growth lines, indicating that they were adding a significant amount of bone mass in a relatively short time frame. This rapid growth is thought to be linked to their need to quickly reach a size where they could compete with adults for food or defend themselves from predators. Interestingly, the pattern of growth lines varies considerably between different dinosaur groups. Ornithischian dinosaurs, the plant-eating dinosaurs like Stegosaurus and Triceratops, often displayed a different growth pattern. Their bones typically show a more consistent, gradual growth rate throughout their lives, suggesting a slower, more deliberate pace of development. This could be linked to their herbivorous diet, which may have required a more prolonged period of maturation and adaptation. Furthermore, scientists are now looking at the microstructure of the growth lines themselves. The spacing and density of the lines aren't just a reflection of overall growth rate. They also relate to the quality of the bone tissue. Dense, closely spaced growth lines indicate rapid growth with a high proportion of immature bone tissue, while sparser lines suggest a slower growth rate and a greater proportion of mature bone. This information is crucial for determining when a dinosaur reached skeletal maturity and when it was at its strongest. The study of growth lines isn't just about estimating lifespans. It also provides insights into dinosaur behavior and environment. For example, researchers have found evidence of periods of stunted growth in certain dinosaur populations, possibly due to nutritional stress or environmental changes. Analyzing these growth patterns can help us understand how dinosaurs responded to challenges, such as droughts or volcanic eruptions. Another exciting development is the application of mathematical models to analyze growth line data. Scientists are developing algorithms that can automatically measure and interpret growth line patterns, allowing for more precise and objective estimates of growth rates. These models can also be used to simulate dinosaur growth under different environmental conditions, providing a powerful tool for testing hypotheses about dinosaur biology. The study of dinosaur growth rates is a constantly evolving field, and new techniques and discoveries are continually refining our understanding. The level of detail revealed by these ancient bone records is simply astounding. It's not just about knowing how big a dinosaur was. It's about understanding the intricate processes that shaped their lives, from their first tentative steps to their eventual magnificent size. Imagine a young Tyrannosaurus rex, barely larger than a modern horse, its growth lines packed tightly together, a frantic race against time to become a formidable predator. Or consider a gentle, plant-eating Camarasaurus, its growth lines spaced further apart, reflecting a more measured, deliberate pace of development. These subtle differences in bone growth patterns hold the keys to unlocking the secrets of these incredible creatures, offering a window into their lives and a deeper appreciation for their place in the history of our planet. The future of dinosaur paleontology is undoubtedly intertwined with the meticulous study of these incredible bone records, promising even more surprising and illuminating discoveries. The Earth doesn't always tell its stories in neatly stacked bones. Sometimes, the record is etched in sand, in mud, in volcanic ash, in the incredibly detailed impressions left behind by dinosaurs themselves. Paleofossil trackways, as these collections of footprints are known, offer a truly remarkable window into how these giants moved, how they traveled, and even how they interacted with their environment. They're not just a scattering of prints, they're entire narratives of movement preserved for millions of years. The process begins with discovery. Paleontologists, the detectives of the prehistoric world, scour landscapes, deserts, riverbeds, coastal areas, searching for these fragile remnants. Often, erosion plays a crucial role, exposing layers of sediment that once held the tracks. Sometimes, the tracks are revealed by a flash flood, momentarily lifting the sediment and bringing them into view. Once found, the initial job is incredibly delicate, carefully excavating the trackway, ensuring that the surrounding sediment is preserved alongside the prints. This is vital because the surrounding rock layers contain information about the environment, the climate, the vegetation, and even the types of animals sharing the space. What makes trackways so special is the incredible level of detail they can provide. Unlike isolated bones, which often tell us a limited story about a single dinosaur's anatomy, trackways reveal how a dinosaur walked. Paleontologists analyze the spacing between prints, the depth of the impressions, and the shape of the imprints to determine stride length, gait, and even speed. This isn't simply about measuring the distance between footprints. It's a sophisticated process of interpretation. There are several distinct gaits a dinosaur could have employed. A quadrupedal gait, where the dinosaur walks on all four limbs simultaneously, is quite common. However, even within this category, there are variations. Some dinosaurs walked with a direct, straighter-legged gait, meaning their limbs moved in a relatively straight line as they advanced. Others exhibited a more sprawling gait, with their limbs splayed out to the sides, providing greater stability, particularly on uneven terrain. The shape of the footprint itself offers clues. A rounded footprint like that of a stegosaurus suggests a heavier animal moving slowly, while a more streamlined elliptical print like that of a predatory dinosaur implies a faster, more agile movement. The study of trackways also allows us to understand group behavior. Sometimes, multiple trackways are found close together, indicating that dinosaurs traveled in herds. The size and spacing of these trackways can provide estimates of herd size. Furthermore, analyzing the direction of the tracks can reveal migration patterns, where dinosaurs were moving and why. Did they follow seasonal food sources? Were they fleeing from predators? The answers aren't always straightforward, but the trackways provide critical evidence. Beyond the simple act of walking, trackways can reveal surprising details about dinosaur locomotion. For example, the footprints of Dinosaurus, a small ornithopod dinosaur, show a distinctive rock-hopping gait. The small, widely spaced prints are a clear adaptation for navigating rocky terrain, and the slight angle of the feet suggests a deliberate rocking motion to maintain balance. This demonstrates a level of behavioral complexity that wasn't always apparent from studying bone fossils alone. The study of trackways isn't just about individual dinosaurs. It provides valuable insights into paleoecology, the study of ancient ecosystems. By analyzing the types of tracks found in a particular area, paleontologists can reconstruct the food web of that environment. For instance, the presence of large, heavily impressed tracks alongside smaller, more delicately defined prints might indicate the presence of a large herbivore followed by smaller predators. The distribution of tracks can even reveal details about the landscape itself. The presence of rivers, swamps, and exposed rock formations. Interestingly, trackways can be affected by environmental factors beyond simply the dinosaur's movement. Rain, for example, can cause the tracks to become distorted, blurring the details and making interpretation more challenging. Conversely, the drying process can solidify the tracks, creating exceptionally well-preserved impressions. The type of sediment in which the tracks are found also plays a crucial role. Fine-grained sediments, like mudstone, tend to produce more detailed impressions than coarser sediments, like sandstone. Analyzing trackways is an ongoing process, and new discoveries are constantly refining our understanding of dinosaur movement. Advances in technology, such as 3D scanning and computer modeling, are allowing paleontologists to create incredibly accurate reconstructions of dinosaur locomotion. These reconstructions aren't just artistic representations. They're based on rigorous scientific analysis of the fossil evidence. Furthermore, the study of trackways is interdisciplinary, drawing on expertise from fields like geology, biomechanics, and computer science. Geologists analyze the surrounding rock layers to understand the environmental conditions at the time the tracks were formed. Biomechanists use computer models to simulate dinosaur movement and test hypotheses about how dinosaurs generated power. Computer scientists develop algorithms to analyze complex trackway data and create detailed 3D reconstructions. Ultimately, the study of dinosaur trackways offers a unique and compelling way to connect with these extinct giants. They are a testament to the power of observation, the importance of meticulous analysis, and the incredible ability of the Earth to preserve even the faintest traces of life. They remind us that even the smallest imprint can tell a vast and fascinating story. The world was a vibrant, noisy place 66 million years ago. Giant long-necked sauropods munched on towering ferns, armored ankylosaurs defended themselves with incredible clubbed tails, and packs of velociraptors hunted smaller prey across vast, lush landscapes. The reign of the dinosaurs was seemingly unchallenged, a period of incredible biodiversity and evolutionary success. But this golden age was destined for a swift and dramatic end, a cataclysmic event that reshaped life on Earth, an event scientists call the Cretaceous Paleogene, KPG extinction event. It wasn't a gradual decline, but a sudden, devastating wipeout, and determining exactly how it happened is one of the most captivating mysteries in paleontology. For decades, scientists wrestled with the evidence, sifting through layers of sediment, analyzing fossil distributions, and using computer models to reconstruct the conditions that led to this extraordinary shift. The initial and ultimately dominant theory centered around a massive asteroid impact, a theory now supported by an overwhelming amount of data. This theory began to take shape in the 1980s, thanks to the meticulous work of Luis Alvarez, his son Walter, and Frank Penrose. They examined a peculiar clay layer found at several locations worldwide, a layer remarkably enriched with iridium, an element that is rare on Earth's surface but surprisingly abundant in asteroids. This iridium layer, discovered first in Gubbisdale, England, and then in Montana, Argentina, and Mexico, was a crucial piece of the puzzle. The Alvarez team proposed that a large asteroid, estimated to be around 10-15 kilometers in diameter, slammed into what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, a massive depression nearly 180 kilometers in diameter and 300 meters deep. The force of the impact was colossal, instantly vaporizing rock and triggering earthquakes and tsunamis of unimaginable scale. Dust, debris, and sulfate aerosols were blasted high into the atmosphere, blocking out sunlight for months, perhaps even years. This blockage is considered the primary driver of the extinction, as plants, the base of the food chain, would have been unable to photosynthesize, leading to a collapse of the entire ecosystem. Furthermore, the impact would have ignited widespread wildfires, adding to the devastation. The sheer energy released was equivalent to billions of times the energy of the Hiroshima bomb. However, the asteroid impact theory isn't the whole story. Scientists now recognize that other factors likely contributed to the extinction, primarily through the role of extensive volcanic activity occurring during the late Cretaceous period. The Deccan Traps, a massive volcanic province located in present-day India, were experiencing a period of intense basaltic eruptions. These eruptions released enormous quantities of greenhouse gases, like carbon dioxide, into the atmosphere. These gases would have significantly altered the climate, contributing to global warming and ocean acidification. The sheer volume of volcanic material ejected into the atmosphere could have further exacerbated the effects of the impact-induced dust cloud, creating a double whammy of environmental stress. The timing of the Deccan Traps eruptions is particularly important. They were active throughout the late Cretaceous, potentially weakening ecosystems already stressed by the impact. It's believed that the volcanic activity also played a role in triggering landslides and destabilizing coastal areas, further amplifying the destructive power of the impact's associated tsunamis. The combination of the asteroid impact and the Deccan Traps volcanism created a truly apocalyptic scenario. The environmental consequences were far-reaching and complex, with feedback loops further intensifying the crisis. For example, the increased carbon dioxide levels would have led to warming temperatures, which in turn would have affected ocean currents and weather patterns. The The debate isn't about whether an impact occurred, because the evidence is overwhelming. It's about the relative importance of the impact versus volcanism and the extent to which these two forces interacted. Some models suggest that the impact triggered the Deccan Trap's eruptions, while others propose the reverse, that the volcanic activity primed the Earth for a catastrophic impact. It's likely a complex interplay of both events, with the impact acting as the immediate trigger and the volcanism amplifying the long-term effects. Furthermore, climate change itself, independent of the impact and volcanism, was already underway. Changes in sea level, shifts in continental positions, and variations in atmospheric composition were influencing the climate and the distribution of plant and animal species. These pre-existing environmental stresses may have made ecosystems more vulnerable to the extreme conditions created by the KPG event. It's also increasingly being considered that some species, particularly smaller ones, were simply unable to adapt quickly enough to the rapidly changing conditions. The KPG extinction wasn't just a mass die-off, it was a transformative event. It paved the way for the rise of the mammals, which had previously been relegated to a subordinate role in the dinosaur-dominated world. With the dinosaurs gone, mammals were free to diversify and eventually evolve into the dominant life forms we see today. The story of the KPG extinction is a powerful reminder of the fragility of ecosystems and the profound influence that cosmic events can have on the history of life on Earth. It's a story of destruction, but also of opportunity, a testament to the resilience of life and its remarkable ability to adapt and survive even the most devastating catastrophes. The world of dinosaurs wasn't just a collection of gigantic, solitary creatures. As paleontologists painstakingly uncover and study fossil discoveries, a far more complex and fascinating picture of dinosaur social behavior is emerging, revealing surprising levels of coordination and interaction. It's like uncovering a secret world of dinosaur families and strategies, vastly different from what we might initially assume based on their immense sizes. The key lies in recognizing that dinosaurs, particularly herbivores, frequently lived in groups, and this wasn't simply about finding enough food, though that was certainly a factor. Early investigations often focused on large sauropods like Brachiosaurus and Apatosaurus, and the incredible fossil trackways we've discovered. These tracks, preserved in fine-grained sediment, sometimes show hundreds, even thousands of individual footprints, suggesting massive congregations. Initially, scientists questioned whether these were just accidental overlaps. However, further analysis, combining trackway patterns with fossil finds of bone fragments, has pointed towards the unmistakable signs of herd behavior. The spacing between footprints isn't random. It indicates a deliberate movement pattern, a kind of traffic flow within the group. Some researchers believe these herds utilized a spiral formation, moving outwards from a central point, which would have been incredibly efficient for covering large areas and searching for new food sources. The sheer scale of these movements, based on trackway analysis, is staggering. Beyond the large herbivores, evidence of smaller, more tightly knit social groups is mounting. Fossils of Velociraptor, famously portrayed in popular culture as cunning hunters, demonstrate a different kind of social structure. While solitary hunting is certainly a part of their story, fossil discoveries reveal they often operated in small packs, typically consisting of 3–6 individuals. The bone beds associated with these Velociraptor remains show that they weren't just killed in one fell swoop. Many individuals died simultaneously, possibly due to a coordinated attack or a landslide triggered by a group pursuit. The size of the bone bed strongly suggests a cooperative hunting strategy, with individuals working together to bring down larger prey. Analyzing the physical characteristics of juvenile dinosaurs provides further clues. Several species, like certain Parasaurolophus individuals, exhibit healed fractures that are consistent with having been treated by others in the group. This suggests a level of caregiving behavior, with older, stronger individuals assisting younger ones who had sustained injuries. The presence of juvenile bones alongside adult remains indicates a family-based structure, with adults protecting and nurturing the young. It's a surprisingly familiar pattern echoing social structures we see in many modern animals, from elephants to primates. The question of cooperative hunting among dinosaurs is particularly intriguing, and remarkably, some fossil evidence lends credence to the idea. Fossil discoveries of Oviraptor have shown a remarkable instance of what scientists call secondary brooding. A single Oviraptor mother was found nesting with the fossilized remains of 6 juvenile Oviraptor chicks. This indicates that the adult Oviraptor likely guarded the nests and protected the young from predators. However, a more provocative discovery involved the potential cooperative killing of a Gallimimus, a swift, ostrich-like dinosaur. A fossil find revealed several Gallimimus individuals surrounding a dying Edmontosaurus, a large hadrosaur, with marks consistent with being driven into a cliff face. This doesn't definitively prove cooperative hunting, but it's a compelling possibility, suggesting a coordinated effort to overwhelm and subdue a much larger opponent. Understanding dinosaur social behavior isn't just about reconstructing their lives. It fundamentally changes our understanding of their intelligence and capabilities. It challenges the long-held view of dinosaurs as simple, instinct-driven animals. Instead, we're beginning to see evidence of sophisticated communication, strategic planning, and even altruistic behaviors, traits previously thought to be exclusive to mammals and birds. The study of dinosaur social behavior is still in its early stages. Paleontologists are continually refining their techniques, using new technologies like 3D scanning and biomechanical modeling to recreate dinosaur movement and social interactions. Each new fossil discovery adds another piece to this complex puzzle. The remarkable diversity of dinosaur social structures suggests that these creatures weren't just surviving, they were thriving, building communities and engaging in behaviors that demonstrate a level of social complexity that continues to amaze and inspire scientists today. The fossil record isn't always clear-cut. Interpretation is key, and paleontologists are always working to refine their hypotheses based on the best available evidence. It's a process of continual investigation, a slow, careful unveiling of a lost world. The story of dinosaur social behavior is far from complete, and it's a story that will undoubtedly continue to evolve as we uncover more secrets from the ancient past. Ultimately, the study of dinosaur social behavior reminds us that life, in all its forms, is often more complicated and nuanced than we initially perceive. It's a reminder of the interconnectedness of life, a testament to the enduring power of community, and a fascinating window into the surprisingly rich and engaging lives of these magnificent creatures that once ruled our planet. The world of dinosaurs wasn't just about colossal size and impressive teeth. It was a world experienced through a remarkably varied set of senses, far more complex than we often picture. Scientists are constantly piecing together clues from fossilized remains, behavioral studies based on fossil evidence, and sophisticated modeling to understand how these ancient giants perceived their surroundings. Let's delve into the fascinating investigation of dinosaur sensory systems, specifically examining their vision, hearing, smell, and a surprisingly intriguing possibility: the ability to sense the Earth's magnetic field. Our understanding of dinosaur vision begins with a key challenge. Fossilized bones don't tell us much about the eyes themselves. However, the shape of the skull, particularly the orbits, the sockets where the eyes would have been, offers a wealth of information. For example, the skull of Tyrannosaurus rex reveals a relatively small, forward-facing eye socket. This suggests that T. rex possessed excellent binocular vision, the ability to judge distances accurately. This was critical for its hunting strategy, enabling it to pinpoint prey with remarkable precision. Larger theropods like Velociraptor often had forward-facing eyes too, a common adaptation among predators requiring good depth perception. Conversely, herbivores like Triceratops had eyes positioned on the sides of their heads, providing a wide field of vision, perfect for spotting approaching danger from all directions. It's believed that their vision was likely less sharp than that of a modern bird of prey, prioritizing overall awareness over detailed sight. The color of a dinosaur's eyes is another area of intense research, although reconstructing it is incredibly difficult. Pigments, like melanin, degrade over millions of years, making it challenging to determine the original color. However, studying the eye socket shape and comparing it to modern birds, which are descended from dinosaurs, provides some clues. Many theropods probably had brown or amber eyes, similar to those of many modern birds. Some researchers hypothesize that certain smaller, feathered dinosaurs might have possessed iridescent eyes, similar to those of peacocks, potentially used for display or communication. The specific shade would have been influenced by the amount of melanin present, a substance that protects against bright light and also plays a role in color. Now, let's turn our attention to hearing. Fossilized dinosaur ear bones, the inner ear structures known as the petrosals, have been found in several crucial dinosaur species, including Velociraptor and Deinonychus. These fossils provide astonishing detail about how these dinosaurs heard. The shape and size of the petrosals are remarkably similar to those of modern birds, suggesting a close evolutionary relationship. This means that many theropods likely had a sophisticated auditory system, able to detect a wide range of frequencies, including high-pitched sounds vital for detecting the rustling of prey or the alarm calls of other dinosaurs. The inner ear structure also indicates a likely ability to localize sound, just as it does in birds today, helping them pinpoint the source of a noise. It's even possible some smaller dinosaurs, especially those with feathers, possessed a complex system for processing sound, enhancing their agility and coordination. Perhaps the most surprising area of research concerns dinosaur smell. Fossilized nasal passages have occasionally been discovered, offering limited but valuable information. The size and shape of these passages suggest that many dinosaurs possessed a well-developed sense of smell, far superior to what we often assume. Scientists have discovered evidence suggesting that some dinosaurs, particularly those related to birds, possessed a vomeronasal organ, a specialized sensory structure that detects pheromones, chemical signals, and other airborne molecules. This organ, located in the roof of the mouth, would have allowed them to detect potential mates, track prey, and navigate their environment. The specific sense they were most sensitive to likely differed greatly depending on the species and its ecological niche. Larger herbivores, for instance, might have been particularly sensitive to volatile organic compounds released by plants, allowing them to find food resources efficiently. However, the possibility of magnetoception, the ability to sense the Earth's magnetic field, is generating considerable excitement. Several lines of evidence suggest that some dinosaurs, particularly those closely related to birds, may have possessed this extraordinary ability. Fossils of Oviraptor and Deinonychus show unusual patterns of growth rings in their bones, which don't align with seasonal temperature variations as expected. Instead, they seem to correlate with the Earth's magnetic field strength. Furthermore, some scientists have discovered magnetite, a magnetic mineral, within the inner ear structures of these dinosaurs, similar to the material found in the inner ears of modern birds. The prevailing theory is that these dinosaurs used the Earth's magnetic field as a kind of internal compass, aiding in navigation, particularly during migration, which is now widely accepted as a key part of the evolutionary story of birds. The exact mechanism of how this works is still being investigated, but it's believed that magnetite crystals within the inner ear respond to changes in the magnetic field, providing the dinosaur with directional information. This capacity would have been especially useful for homing in on nesting sites or for long-distance journeys. Ultimately, reconstructing the sensory world of dinosaurs is a complex undertaking, a puzzle built from fragments of evidence. While we may never know exactly how a T-Rex experienced the world, continued research, fueled by increasingly sophisticated analytical techniques, is slowly revealing the fascinating and often surprising ways in which these magnificent creatures perceived their surroundings. The fossil record of dinosaur teeth is a truly remarkable chronicle of dietary change, a silent testament to millions of years of adaptation and specialization. It's far more complex than simply big teeth for chewing tough plants. The story begins with the earliest herbivores, the sauropodomorphs like Platysaurus, and reveals a breathtaking diversity of tooth arrangements, each sculpted by the demands of their particular food sources. These early giants, resembling a cross between a crocodile and a lizard, possessed peg-like teeth, small, bluntly pointed structures arranged in a single dental battery. This battery, a row of teeth, was constantly replaced throughout the dinosaur's lifetime, a process called tooth replacement. The teeth were not designed for prolonged grinding. Instead, they were used for stripping leaves from branches, a quick and efficient way to access vegetation. The arrangement, though simple, suggests a diet focused on soft, young foliage. As we move forward in time, we see a significant shift in the evolutionary trajectory of herbivore teeth, particularly with the rise of the large sauropods like Brachiosaurus and Apatosaurus. These colossal creatures demanded a vastly different approach to feeding. Their dental batteries became increasingly complex, evolving into a cone-shaped arrangement. This change wasn't just a cosmetic one. It reflected a dietary shift towards tougher, fibrous plants. The cone shape allowed for a shearing action, effectively slicing through resilient ferns and cycads. The tooth replacement process remained crucial. Each tooth was replaced as it wore down, ensuring the animal could continuously access its food. Interestingly, the size of the tooth battery often correlated with the size of the dinosaur itself, reflecting the sheer volume of plant matter needed to sustain such enormous bodies. The evolution of herbivore teeth took an even more intricate turn with the emergence of ornithopods like Iguanodon and Hadrosaurus. These dinosaurs, often depicted with elaborate, duck-like beaks, possessed dental batteries characterized by a shovel-shaped morphology. This arrangement wasn't a single, uniform design. It varied considerably across different ornithopod species. Some, like Iguanodon, had batteries with broad, flattened teeth, ideal for cropping down low-growing vegetation such as rushes and ferns. Others, such as Hadrosaurus, had batteries with more pointed, blade-like teeth, allowing them to effectively process tougher, more abrasive plant material, possibly including seeds and conifer needles. The presence of bone-crushing elements within the dental battery of certain hadrosaurs has been identified through fossilized remains, demonstrating a surprisingly adaptable diet capable of processing bones, likely for obtaining calcium and other nutrients. The ceratopsians, the horned dinosaurs like Triceratops, present a particularly fascinating case study in dental evolution. Their dental batteries were remarkably specialized, consisting of numerous, closely packed teeth arranged in a wedge or shovel shape. These teeth weren't designed for chewing. Instead, they were primarily used for stripping leaves from branches, much like the early sauropodomorphs. The complex interlocking arrangement of the teeth would have provided a strong grip, allowing them to pull branches toward their mouths. The wear patterns on the teeth show a distinct preference for softer vegetation, and the lack of significant bone-crushing elements indicates a primarily folivorous diet. Furthermore, the variation in tooth shape and size across different ceratopsian species likely reflected differences in their feeding habits and the types of plants they consumed. Moving to the hadrosaurs again, we observe a stunning diversity within the dental battery. The shovel-shaped teeth were incredibly adaptable. Some hadrosaurs, such as Edmontosaurus, had teeth with sharp, blade-like edges designed for cropping vegetation from the ground. These were ideally suited for feeding on low-lying ferns and cycads. Other hadrosaurs, like Maiasaura, possessed teeth with more rounded edges and complex wear patterns, suggesting they specialized in feeding on tougher, more abrasive plant material, possibly including coniferous needles and woody stems. The constant replacement of teeth was critical for maintaining the effectiveness of these specialized dental batteries throughout their long lives. It's important to remember that the analysis of dental batteries isn't just about counting teeth. The shape of the teeth, the wear patterns on the enamel, and the arrangement of the battery provide invaluable clues about the animal's diet, feeding behavior, and even its ecological niche. The study of tooth replacement rates also offers insights into dinosaur growth rates and lifespan. Essentially, the fossilized teeth of these ancient herbivores provide a window into their lives, revealing a remarkable story of adaptation, specialization, and the enduring relationship between dinosaurs and the plants they consumed. Analyzing these intricate dental batteries continues to reshape our understanding of dinosaur behavior and the evolutionary forces that shape these magnificent creatures. The fossil record rarely offers a direct glimpse into the sounds of the past, but paleontologists are increasingly turning to a fascinating and complex approach, reconstructing dinosaur vocalizations. It's a hugely challenging endeavor, relying heavily on inference, comparative anatomy, and behavioral observations to build a picture of how these magnificent creatures communicated. We know, of course, that dinosaurs possessed a range of anatomical features, suggesting they were capable of producing sound, features largely overlooked in the earlier focus on their physical attributes. The sheer size of many dinosaurs, particularly the larger theropods, implies a resonant vocal apparatus. Their hyoid bones, the small U-shaped bones in the throat that support the tongue and aid in sound production, exhibit a surprising diversity in shape and size across different dinosaur groups. Some, like those found in Tyrannosaurus rex, were elongated and flexible, similar to those seen in modern birds and crocodiles, hinting at the potential for a wide range of vocalizations, including perhaps deep, rumbling calls. Conversely, the more robust, boxy hyoid bones of smaller ornithopods suggest a more restricted vocal range, potentially focused on shorter, sharper sounds. Furthermore, the structure of the larynx, the voice box, remains largely unknown due to the fragile nature of the fossil material. However, analyzing the associated muscles and cartilage provides valuable clues. The presence of the laryngeal sinus, a specialized cavity in the throat, in many theropods is particularly intriguing. This sinus, similar to the syrinx found in birds, would have acted as a resonating chamber, amplifying and shaping the sound produced by the vocal cords. The size and shape of this sinus would have determined the pitch, tone, and volume of the dinosaur's calls. It's reasonable to hypothesize that Tyrannosaurus rex, with its large sinuses, could have produced incredibly powerful roars, sounds capable of intimidating rivals and potentially stunning prey. In contrast, smaller, agile predators like Velociraptor likely possessed smaller, more refined sinuses, enabling them to communicate more subtly, perhaps with chirps, whistles, or even ultrasonic calls, undetectable to the human ear. But reconstructing vocalizations isn't just about the anatomy of the vocal apparatus. Paleontologists are increasingly considering the behavioral context of dinosaur interactions. Evidence from fossil sites reveals complex social behaviors that suggest sophisticated communication strategies. For example, the discovery of numerous Maiasaura nests with associated juveniles indicates a highly cooperative parenting system. These dinosaurs likely used calls to maintain contact with their young, alert others to danger, and coordinate group activities. The sheer number of individuals associated with these nests suggests a vocal communication system was absolutely essential for their survival. Similarly, the fossil record shows instances of multiple dinosaurs feeding together, suggesting a need for coordinated feeding behavior, which would undoubtedly have involved vocal signals. Analyzing the spacing and orientation of fossilized bone beds, where multiple individuals of the same species were buried together, provides an indirect record of social interaction, further supporting the idea of vocal communication. The role of infrasound, extremely low-frequency sound waves, in dinosaur communication is another area of growing interest. Infrasound travels long distances and can pass through obstacles like vegetation, making it an ideal medium for conveying information over large territories. Large herbivores, such as sauropods, may have utilized infrasound to communicate across vast distances, alerting others to the presence of predators or signaling the availability of food. There's even speculation that certain dinosaurs, particularly large theropods, may have been able to produce infrasound, though this remains highly speculative. The challenge is that infrasound is notoriously difficult to detect and study, and our current technology is limited in its ability to recreate the conditions necessary for its propagation and analysis. Beyond simple calls, it's plausible that dinosaurs developed more nuanced forms of communication. The discovery of fossilized feathers, particularly in theropods, hints at the possibility of visual displays, postures, movements, and coloration being integrated with vocalizations. Perhaps a raised crest, combined with a specific call, served as a signal of aggression, while a slower, deliberate movement accompanied by a gentle rumble indicated reassurance. The complexity of these integrated signals would have been far greater than simple vocalizations alone. Furthermore, the study of animal vocalizations in modern birds and reptiles provides valuable insights. Many reptiles, including crocodiles and lizards, produce a remarkable array of sounds, from deep bellows to high-pitched chirps. These sounds are used for a variety of purposes, including attracting mates, defending territory, and communicating with conspecifics. By comparing these sounds to the anatomy and behavior of dinosaurs, paleontologists can formulate informed hypotheses about the types of vocalizations produced by these extinct creatures. It's important to note that while we can't definitively hear what a dinosaur sounded like, we can use our knowledge of animal behavior and physiology to build a compelling and increasingly detailed picture of their communication strategies. The quest to unlock the sounds of the past is a continually evolving scientific endeavor, driven by technological advancements and a deeper understanding of the remarkable adaptations of these ancient giants. The world of dinosaurs wasn't just about roaring giants and immense scales. It held a secret, a surprisingly tender story of parental involvement. For a long time, paleontologists assumed dinosaurs were solitary creatures, driven solely by instinct to hunt and reproduce. However, increasing evidence is slowly revealing a far more nuanced picture, one where many dinosaur species invested significantly in their young, shaping their early lives in ways that echo, in some respects, our own modern behaviors. This investigation begins with the discovery of nesting sites, offering glimpses into the complex routines of dinosaur families. The first real clues came from remarkably preserved fossil nests found across various continents. In Mongolia, scientists unearthed a cluster of nests belonging to Oviraptor, a dinosaur once thought to be a meat-eater, now recognized as a likely omnivore. These weren't simple piles of eggs. They were meticulously constructed structures, often built within depressions in the ground, reinforced with surrounding vegetation, and sometimes lined with feathers, suggesting a deliberate attempt to provide warmth and protection. Similar nests, constructed with similar care, have been identified with Troodon, another intelligent dinosaur species, revealing a pattern of behavioral investment. The scale of these nests varied, with some holding just a few eggs, while others belonging to larger theropods contained dozens. This indicates a range of parental investment linked to the size of the offspring. Beyond the nests themselves, fossil evidence of egg care is becoming increasingly compelling. The famous Raptorex fossil, nicknamed Mary, provided an exceptional example. Mary's skeleton was discovered with a fossilized egg clutched in her foot, suggesting she may have been guarding her nest. More recently, in Utah, researchers discovered a nearly complete velociraptor nest containing numerous fossilized eggs. Furthermore, analyses of fossilized eggshell fragments, particularly those from hadrosaurs, duck-billed dinosaurs, have revealed intriguing details. Scientists have identified micro-scratches on the eggshells, indicating that young dinosaurs were actively nipping at them, likely trying to break through the shell to access the yolk. This suggests a level of interaction between parent and offspring before hatching. The interpretation of these findings isn't straightforward, of course. The precise nature of parental care varied dramatically between dinosaur groups. Some, like Oviraptor, appear to have actively incubated their eggs, possibly using their bodies to generate warmth, especially in cooler climates. The precise function of the feathers found within these nests is still debated. They might have been used for insulation, nest building, or even for a rudimentary form of parental contact. Other dinosaurs, such as ceratopsians, horned dinosaurs, likely provided only minimal protection, perhaps simply staying nearby while their young hatched. Perhaps the most surprising aspect of dinosaur parental care concerns juvenile survival rates. The fossil record provides stark evidence of how precarious life was for young dinosaurs. While some species, particularly smaller theropods, exhibited relatively high survival rates, many larger dinosaurs had exceptionally low juvenile mortality. The fossil evidence paints a picture of immense struggle. Remains of juvenile Tyrannosaurus rex, for example, are remarkably rare, suggesting that only a small fraction of these massive creatures made it past their first few years. The reasons for these low survival rates are complex and likely included a combination of factors. Predation was undoubtedly a major threat. Juvenile dinosaurs, lacking the size and defenses of adults, were vulnerable to attack by larger predators. Moreover, many dinosaur species lived in crowded environments, increasing the risk of disease transmission. Competition for food was also intense, particularly among young dinosaurs striving to establish their territories. Furthermore, the fossil record demonstrates that juvenile dinosaurs were often dwarfed by their parents, making them physically weaker and less able to defend themselves. This physical disadvantage, combined with the other challenges they faced, resulted in a high degree of natural selection against young dinosaurs. The bones of juvenile dinosaurs frequently show signs of injury, indicating that they were frequently involved in fights or were victims of accidents. Despite these challenges, the evidence increasingly supports the idea that many dinosaur species actively shaped the lives of their young. The discovery of parental care is changing our understanding of these magnificent creatures, moving them beyond the realm of simple instinct and suggesting a level of behavioral sophistication that is truly remarkable. As paleontologists continue to uncover new fossil evidence, we can anticipate even greater insights into the complex and, at times, heartbreaking story of dinosaur parental care, adding another layer of depth to our understanding of these ancient giants. The search for more clues continues, promising a more complete picture of the lives of these incredible animals. The Earth during the Mesozoic era wasn't just a collection of dinosaurs roaming the land. It was a bustling, incredibly complex web of life. Understanding dinosaurs requires us to step back from individual species and consider their place within these immense ecosystems. Scientists now recognize that dinosaurs, both herbivores and carnivores, were absolutely fundamental to shaping the landscapes and influencing the evolution of countless other organisms. It's a story of interconnectedness, a delicate balance constantly shifting due to the sheer scale and impact of these ancient creatures. Initially, the prevailing thought was that dinosaurs were simply large animals occupying vacant niches. However, Accumulating evidence reveals a far more intricate relationship between dinosaur populations and the world around them. The investigation began with mapping out food webs, visualizing who ate whom, and how energy flowed through the system. Paleontologists use fossil finds, analyzing tooth wear patterns, fossilized dung coprolites, and even the shape of bones to reconstruct these complex networks. For instance, the presence of large, heavily worn teeth on theropods like Tyrannosaurus rex indicates a diet of incredibly tough, fibrous plant matter, possibly cycads and conifers, alongside the bones of massive herbivores. Conversely, the sharp, serrated teeth of smaller theropods suggest a more varied diet, likely including smaller dinosaurs, reptiles, and possibly even large insects. Herbivores, of course, were the foundation of these ecosystems. Sauropods, such as Brachiosaurus and Diplodocus, were the giants, consuming enormous quantities of vegetation. Their grazing habits profoundly impacted plant communities. The sheer weight of these animals compacted soil, facilitating seed germination and allowing smaller plants to thrive. Furthermore, their movement continuously uprooted and redistributed plant matter, creating patches of open grassland, a key feature of many late Jurassic and early Cretaceous environments. The study of fossilized plant stems, often flattened and distorted, directly links back to the grazing pressures exerted by dinosaurs. Scientists can even estimate the volume of vegetation consumed by a herd of Parasaurolophus, based on the size and distribution of fossilized plant remains found in their feeding grounds. Predation relationships weren't simply about the big predators like T-Rex bringing an end to their prey. The presence of large carnivores created a selective pressure on herbivores, leading to the evolution of defensive adaptations. Many herbivores developed thicker armor, the bony plates of ankylosaurs, the robust frills of ceratopsians, not just for protection against predators, but also to enable more efficient browsing. The need to avoid becoming a meal shaped the evolution of speed and agility in many dinosaur groups, allowing them to outrun or evade threats. Smaller predators, like Velociraptor, likely played a role in controlling populations of smaller herbivores and insects, preventing any single species from dominating an area. The fossil record shows numerous instances of dinosaur skeletons found near the remains of their prey, providing stark visual evidence of these hunting behaviors. But the impact of dinosaurs extended far beyond direct predation. The distribution and abundance of plant life was dramatically altered by dinosaur activity. Large herbivores, as we've discussed, sculpted landscapes, creating and maintaining open spaces. The frequent trampling by dinosaurs also exposed seeds to sunlight, a critical step in plant reproduction. Interestingly, some scientists believe that dinosaur dung itself played a significant role in nutrient cycling. Coprolites are rich in organic matter and contain identifiable plant remains, providing a direct record of the dinosaur diet and, consequently, the types of vegetation available. Analyzing coprolites allows researchers to reconstruct past environments with astonishing detail. Furthermore, dinosaur presence influenced the evolution of plant defenses. Plants developed thorns, spines, and chemical defenses to deter dinosaur browsing. The very morphology of many plant species, their leaf shapes, stem structures, demonstrates an evolutionary response to dinosaur grazing pressure. In some regions, plant communities evolved to be less palatable to dinosaurs, favoring plants that were difficult for them to consume. This created a feedback loop. Dinosaurs adapted to eat certain plants, which in turn led to the evolution of even tougher, more resilient plant defenses. The story of dinosaur impact isn't just about destruction. It's about a continuous evolutionary arms race between herbivores and plants. The study of dinosaur ecosystems also highlights the importance of considering the broader environmental context. Climate, geography, and the availability of resources all played a role in shaping dinosaur populations and their interactions with the surrounding environment. For instance, the arid conditions of the late Cretaceous likely favored the evolution of drought-resistant plants, which in turn influenced the distribution and behavior of dinosaur herds. Paleoenvironmental data, gathered from pollen analysis and sedimentary records, provides a crucial layer to understanding these interactions. It's important to remember that the Mesozoic era wasn't a static period. It was a time of dramatic environmental change, and dinosaurs were inextricably linked to these changes. Ultimately, understanding dinosaurs within their ecosystems provides a far richer and more nuanced picture of life on Earth millions of years ago. They were not merely isolated creatures, but integral components of complex and dynamic systems. Their impact shaped the landscapes, influenced the evolution of countless other organisms, and ultimately helped to create the world we inhabit today. The ongoing investigation of dinosaur ecosystems continues to reveal new insights into the interconnectedness of life and the profound influence of these ancient giants. It's a story of survival, adaptation, and the beautiful, intricate balance of nature. A reminder that even the most powerful creatures are part of a larger, interconnected web. The shifting sands of the late Cretaceous held secrets not just of immense size and terrifying teeth, but of incredibly complex bodies. Paleontologists, using a blend of fossil analysis, biomechanical modeling, and comparisons with modern reptiles and birds, are slowly piecing together how dinosaurs, specifically, several key groups, actually worked. Let's delve into the fascinating physiology of these ancient giants, focusing on their cardiovascular systems, respiratory systems, and digestive systems. The tyrannosaurids, like Tyrannosaurus rex, present perhaps the most dramatic cardiovascular puzzle. These apex predators were built for explosive bursts of speed, followed by sustained, powerful strides. The bones themselves, particularly the massive femur, suggest a robust skeletal structure designed to handle tremendous forces. However, conventional models of their hearts, based solely on size comparisons to modern animals, were often inadequate. Recent studies, incorporating biomechanical simulations, have proposed a significantly larger heart than initially anticipated, possibly with a thicker myocardium, the heart muscle itself, to efficiently pump blood to their powerful muscles during those short, intense chases. Furthermore, evidence from fossilized blood vessels, though rare, hints at a highly specialized circulatory system, potentially with multiple arterial branches directly supplying the legs and jaws, maximizing oxygen delivery where it was needed most. The sheer size of the T-Rex's legs indicates a massive demand for oxygen, and the heart's capacity likely evolved to meet this need, allowing for these incredible bursts of power. Moving to the ceratopsians, the horned dinosaurs like Triceratops, reveals a markedly different physiological strategy. These herbivores needed to maintain a constant, sustained level of activity while consuming vast quantities of vegetation. Their skeletal structure, though heavily built, wasn't designed for the same bursts of speed as the tyrannosaurs. Instead, researchers believe their cardiovascular systems were optimized for endurance. The shape of the vertebrae, coupled with the inferred muscle attachments, suggests a reliance on slow, deliberate movements. The heart, consequently, would have been smaller and less powerfully built, emphasizing efficiency over brute force. Furthermore, the ceratopsians possessed a proportionally larger nasal cavity, offering a significant increase in surface area for gas exchange, a critical component of their respiratory system. Analysis of fossilized bone structure has revealed a network of capillaries closely associated with the nasal passages, acting as a shortcut for oxygen directly into the bloodstream, particularly beneficial during periods of exertion like browsing or defense. The nasal passages weren't merely for smelling, they were vital organs for sustaining life. The ornithomimids, swift, bird-like dinosaurs such as Ornithomimus, present another captivating case. These dinosaurs, renowned for their speed and agility, possessed a respiratory system remarkably similar to that of modern birds. They lacked the heavy, cumbersome rib cage associated with many other dinosaurs, a key adaptation that simplified breathing. Their sternum, the breastbone, was unusually lightweight and lacked the extensive connection seen in larger dinosaurs, allowing for greater flexibility and a more efficient exchange of gases. The fossilized evidence, particularly the delicate structure of the ribs, indicated a one-way airflow system, like that found in birds, where air moved in a single direction through the lungs. This system minimizes dead space, the volume of air that doesn't participate in gas exchange, dramatically improving the efficiency of respiration. Coupled with their lightweight skeleton and likely fast-paced lifestyle, this system allowed them to sustain high activity levels with minimal energy expenditure. The rhythmic pumping action of their heart, driven by a relatively simple valve structure, supported this efficient breathing. Now, let's consider the digestive systems of the hadrosaurs, the duck-billed dinosaurs, a group renowned for their specialized teeth and enormous size. The sheer volume of plant matter they consumed demanded a truly remarkable digestive system. Analysis of fossilized stomach contents, though rarely preserved in exceptional detail, has yielded tantalizing clues. Researchers believe that hadrosaurs possessed a multi-chambered stomach, similar to that found in modern birds and reptiles. This intricate system allowed them to efficiently extract nutrients from tough plant material, breaking down cellulose, the primary component of plant cell walls, through a process of fermentation aided by symbiotic bacteria. The stomach chambers would have acted like a biological churn, mechanically breaking down food and facilitating microbial digestion. The heart, consistently pumping blood to the stomach, fueled this microbial fermentation, vital for obtaining energy from the plants they consumed. Interestingly, the shape and arrangement of the ribs provided considerable abdominal space, facilitating the expansion necessary for this complex digestive process. The evolutionary pathways for these vastly different dinosaur physiologies illustrate a remarkable adaptability. Each group had evolved unique solutions to the challenges of their environment and lifestyle. The Tyrannosaur's powerful heart and circulatory system supported bursts of speed, while the ceratopsians prioritized endurance. The ornithomimids optimized for agility and efficient respiration, and the hadrosaurs harnessed fermentation for optimal plant digestion. Studying these differences and the common threads of evolutionary innovation allows us to not just admire the impressive size and power of these extinct creatures, but also to appreciate the intricate biological systems that sustain their existence. It's a reminder that dinosaur physiology wasn't simply about being gigantic, it was about being exquisitely designed. The year was 1861. A young German geologist named Gunther Bechlin was meticulously examining rock formations near Königstein am Rhein, a town nestled in the German state of Rhineland-Palatinate. He wasn't looking for enormous, thunderous dinosaurs. That was still a relatively new idea, largely championed by the American paleontologist Othniel Charles Marsh and his colleague Joseph Leidy. Instead, Bechlin was studying a particular type of limestone, a rock known for containing fossilized plant remains. He noticed something peculiar, a small, feather-like structure embedded within the stone, something that didn't quite fit with the known fossil flora. He sketched the find, a delicate, almost brush-like structure, and sent a specimen to Joseph Leidy, a renowned paleontologist at the University of Pennsylvania. Leidy, initially skeptical, recognized the unusual nature of the specimen and, recognizing its potential importance, carefully documented it. It was a remarkable discovery, but its significance wasn't immediately grasped. It was simply labeled a fossil feather. Years passed, and the specimen remained relatively obscure until 1861, when Elias Heilmann, another German geologist, was surveying the same limestone quarry. Heilmann, unlike Leidy, was keenly interested in any unusual fossils, and he too found a similar feather-like structure. He meticulously extracted the fossil, this time including a small reptilian bone alongside the feather. This combined find, designated as JFA1, was then sent to Lady, who was now intensely focused on the specimen. Lady, along with his student Harry Seeley, began to piece together a more complete picture. They realized that this wasn't just a feather. It was the remains of a creature that possessed characteristics of both reptiles and birds. The combination of the feathered structure and the reptilian bone presented a puzzle that challenged the established understanding of life's evolution. The crucial step in recognizing the true significance of JFA1 came in 1863, when Seeley, having left Lady's immediate team, independently examined the fossil. Seeley, a brilliant and insightful student, immediately understood that the creature represented a transitional form, a missing link between the ancient reptiles that dominated the earth for so long and the birds that would eventually fill the skies. He published his findings, describing the fossil as a reptile with feathers. This publication ignited a flurry of interest and debate within the scientific community. Lady, initially hesitant to embrace such a radical concept, eventually conceded that Seeley's interpretation was compelling. The discovery of JFA1, now increasingly recognized as Archaeopteryx, began to reshape the entire field of paleontology. Archaeopteryx wasn't a gigantic dinosaur, as many might initially imagine. It was a relatively small creature, estimated to have been about the size of a crow. Its skeletal structure revealed a fascinating mosaic of features. It possessed teeth, a long bony tail typical of reptiles, and wings with feathers, but these wings were supported by elongated hand bones, just as bird wings are today. The shape of its bones, particularly the wrist, suggested that its wings were used for gliding rather than powered flight, a crucial distinction. Further discoveries of Archaeopteryx fossils, primarily from the Solnhofen limestone of Bavaria, Germany, gradually solidified the understanding of its importance. These subsequent finds revealed variations in size and bone structure, providing a more detailed picture of this remarkable transitional species. The discovery of Archaeopteryx provided the first compelling evidence for the evolutionary connection between dinosaurs and birds. Before Archaeopteryx, the idea of dinosaurs evolving into birds was largely speculative. Archaeopteryx demonstrated that these two groups weren't entirely separate lineages, but rather shared a common ancestor, a reptile that possessed feathers and a grasping hand, features that would eventually evolve into the wings and feet of modern birds. The fossil's preservation was exceptional, a rare occurrence in the fossil record, capturing a moment in time with astonishing detail. The surrounding limestone contained impressions of plants and insects, offering a snapshot of the ancient environment in which Archaeopteryx lived. The initial classification of Archaeopteryx was somewhat challenging. Scientists struggled to fit it neatly into the existing dinosaur or bird categories. It wasn't quite a dinosaur, with its feathers and bird-like anatomy, but it wasn't a fully formed bird either. Lady initially classified it as a dinosaur, while others proposed it as a primitive bird. However, as more fossils were unearthed and analyzed, the consensus grew that Archaeopteryx represented a crucial intermediate stage in the evolutionary transition. It served as a tangible illustration of how complex features could gradually develop over millions of years. The significance of Archaeopteryx extends far beyond its individual features. It revolutionized our understanding of evolution, demonstrating the power of gradual change and adaptation. It highlighted the concept of transitional fossils, organisms that possess characteristics of both ancestral and descendant groups, as a cornerstone of evolutionary theory. The story of Archaeopteryx is a testament to the painstaking work of paleontologists, the importance of careful observation, and the transformative potential of a single, extraordinary fossil. It remains one of the most iconic and influential discoveries in the history of science, continuing to inspire and inform our understanding of life's incredible journey. The Earth holds secrets, silent stories whispered across millions of years. Many of these stories are etched in stone, in the very bones of dinosaurs. But the simple fact is, not every dinosaur skeleton we find is a complete, perfect puzzle. The process of fossilization, how a creature transforms from living flesh into a solid rock record, is a remarkably complex and often fragile one. It's a delicate dance between geological forces and specific chemical reactions, a race against time where conditions must be just right for preservation to occur. Initially, the most common way a dinosaur skeleton begins its journey to becoming a fossil is through rapid burial. A sudden event, like a flash flood caused by a volcanic eruption or a landslide, is frequently responsible. These events can quickly cover a dinosaur, perhaps one that has died in a river or swamp, with layers of sediment, mud, sand, silt, even volcanic ash. This initial burial is absolutely critical. Without it, the soft tissues of the animal would rapidly decompose, leaving behind little to no trace. The sediment acts as a protective shield, preventing exposure to oxygen, which is the biggest enemy of fossilization. Oxygen causes oxidation, the process of rust forming on iron. It does the same thing to organic material, breaking it down into carbon dioxide and water. Once buried, the sediment compacts under its own weight, a process called compaction. This forces out water and air from the pore spaces within the sediment, and the sediment grains begin to squeeze together. As the sediment gets denser, it transforms into sedimentary rock, sandstone, shale, or limestone, depending on the size of the sediment grains and the type of cement that holds them together. The dinosaur's bones, still largely organic material, become embedded within this newly formed rock. However, simply being encased in rock isn't enough. The bones need to be protected from further decay, and that's where chemistry comes in. Several chemical processes contribute to fossilization, but the most significant is mineralization. Over time, groundwater, water rich in dissolved minerals, seeps into the surrounding sediment and comes into contact with the porous surfaces of the dinosaur bones. This groundwater typically contains ions like calcium, magnesium, iron, and silica. These ions react with the organic material in the bone, gradually replacing it with minerals. The precise mechanisms of this mineralization are still being actively researched, and it's not always a straightforward step-by-step process. In some cases, the minerals simply fill the tiny pores and cracks within the bone, strengthening it and making it more resistant to decay. In other instances, the original bone material is completely replaced by minerals, a process known as permineralization. This creates a stone replica of the original bone, often retaining intricate details like muscle attachments and even growth lines. The type of mineral that dominates the replacement process can vary greatly depending on the geological environment. In limestone environments, for example, calcium carbonate, the main component of limestone, is the primary mineral involved, often forming a hard, stony shell around the bone. In shale environments, silica, found in sand and quartz, frequently plays a key role. Iron minerals, particularly pyrite, fool's gold, are common in many fossil-rich areas and can sometimes create spectacular, glittering inclusions within the fossilized bones. The rate of mineralization is also influenced by factors like temperature and pH. Warmer temperatures generally accelerate the process, while acidic conditions can actually promote the breakdown of bone material. It's a delicate balance, and the specific chemical environment within the sedimentary layer dictates the final outcome. Sometimes, a fossilized bone will display a mixture of original organic material and mineral replacement, offering a fascinating glimpse into the stages of the fossilization process. Scientists can even analyze the isotopic composition of the fossilized bone to learn more about the dinosaur's diet and the environment in which it lived. Furthermore, the chance of fossilization isn't just about the immediate burial event. The geological conditions surrounding the fossil also play a crucial role. Areas with active tectonic plate movement, like the Rocky Mountains, tend to have higher rates of uplift and erosion, which can expose fossils to the elements and destroy them before they can be fossilized. Conversely, areas with stable geology and minimal erosion are much more favorable for fossil preservation. The fossilization of soft tissues, skin, feathers, internal organs, is an exceedingly rare event. It requires exceptionally rapid burial and very specific conditions. Some exquisitely preserved fossils have been found with remarkably well-preserved skin impressions, feather traces, and even traces of stomach contents. These discoveries are incredibly rare and provide invaluable insights into the appearance and physiology of extinct dinosaurs. Finally, it's important to acknowledge that fossilization is a statistical improbability. Most dinosaur bones simply decompose over time, returning their elements to the earth. Only a tiny fraction of the dinosaurs that ever lived become fossilized, and even fewer are found and studied. Each fossil represents a unique and remarkable victory against the relentless forces of time and decay. The preservation of a dinosaur skeleton is truly a testament to the power of geological processes and the enduring legacy of these magnificent creatures. The world of dinosaurs wasn't just about immense size and terrifying teeth. It held a fascinating and often perplexing mystery for paleontologists. How did dinosaurs determine their sex? We know so much about their bones, their movements, and their diets, but figuring out whether a particular femur belonged to a male or a female could be a real detective's challenge. Unlike many modern animals, where sex is determined by chromosomes, a simple XX for females and XY for males, dinosaur sex determination seems to have been far more complex, relying on a patchwork of subtle differences etched into their skeletons. Early attempts to determine dinosaur sex were, frankly, a bit haphazard. Researchers would simply measure bones like the length of the femur or the width of the pelvis, and make educated guesses based on the observed differences. It was like trying to guess someone's age just by looking at their hands. Sometimes you get a general idea, but it's rarely precise. This approach, while providing some initial clues, quickly revealed the limitations of simply comparing measurements. For instance, a particularly robust femur might be attributed to a large male, but it could equally belong to a female who was exceptionally strong. The key to a more reliable approach lies in what paleontologists call sexual dimorphism, the distinct differences in size, shape, and ornamentation between males and females of the same species. These differences aren't just about one being bigger than the other. They're about a constellation of changes across the skeleton. The most commonly studied feature is the femur, the large bone in the upper leg. In many large theropod dinosaurs, like Tyrannosaurus rex, males exhibited significantly larger femurs than females. This difference wasn't uniform. The greater trochanter, the large, bulky projection at the upper end of the femur, was noticeably larger in males. This larger projection is thought to have been associated with increased muscle mass, a trait likely crucial for combat or displays of dominance. However, it's vital to remember that sexual dimorphism isn't a universal rule. In some groups, like certain ornithopods, the duck-billed dinosaurs, the differences between male and female femurs were much more subtle, sometimes almost imperceptible. Researchers have also examined the pelvis, which shows variations in the size and shape of the acetabulum, the socket where the femur sits. Males often possessed a deeper and wider acetabulum, offering greater stability for powerful movements. Furthermore, the size and shape of the neural arches, the bony projections that support the vertebrae, can also vary between sexes, potentially related to muscle attachment and strength. Beyond the long bones, paleontologists have explored other indicators of sex. Fossilized teeth, for example, can reveal differences in size and shape. In some ceratopsians, horned dinosaurs like Triceratops, males often had larger, more robust teeth, suggesting a greater need for grappling or combat. The skull itself can also exhibit sexual dimorphism. researchers have found differences in the size and shape of the nasal bones, the brain case, and even the horns in some species. Analyzing the arrangement of bone tissue, known as osteological markers, is a burgeoning area of research. These markers, often created during growth, can reflect differences in hormone exposure and, consequently, sex determination. The investigation of fossilized skin impressions has recently added another layer of complexity to this puzzle. Some dinosaur species have produced remarkably detailed skin impressions, allowing researchers to observe variations in skin texture and patterns. While the direct link between these patterns and sex is still being investigated, there's a growing suspicion that some patterns might have played a role in courtship displays or mate recognition. Imagine, if you can, a dinosaur species where specific markings on their skin signaled their readiness to mate, a visual communication system lost to time, yet potentially detectable in the fossil record. Another area of intense study is the investigation of bone microstructure. Using techniques like micro-CT scanning, researchers can examine the intricate patterns of bone tissue formation. These patterns can reveal changes in bone growth rates, which are influenced by hormones. The discovery of sex-specific patterns in bone growth is a particularly exciting development, offering a more direct way to link hormone exposure to skeletal changes. The challenge remains, however, that many dinosaur fossils are incomplete. A missing femur, a fragmented pelvis, or a damaged skull can make it incredibly difficult to determine a dinosaur's sex with certainty. Furthermore, the extent of sexual dimorphism can vary significantly between species, and even within a single species over time. Some dinosaur populations may have shifted their morphology in response to environmental pressures or changes in social dynamics. Ultimately, reconstructing dinosaur sexual lives is a painstaking process, a collaboration between geology, paleontology, and increasingly detailed analyses of microscopic bone structures. It's a reminder that even the most imposing creatures, the giants of the Mesozoic era, possessed a hidden complexity, a secret language etched into their bones, waiting to be deciphered by future generations of scientists. And perhaps, one day, we will fully understand the intricate dance of courtship, competition, and survival that shaped the lives of these magnificent extinct animals. The world of dinosaurs wasn't just one of towering giants and fearsome predators. It was also a place where the seeds of intelligence were being sown. For a long time, scientists believed that dinosaurs, particularly the larger ones like the Tyrannosaurus rex, were simply driven by instinct, powerful muscles, and teeth dictating their actions. However, recent discoveries and increasingly sophisticated research methods are revealing a much more nuanced picture, one where certain dinosaur lineages possessed remarkable cognitive abilities, challenging our long-held assumptions about their behavior. It began with a shift in how paleontologists approached fossil evidence, moving beyond just size and physical characteristics to meticulously analyzing the details of braincase morphology and searching for traces of complex behaviors. The first crucial step was examining the shape of the dinosaur braincases, the skulls containing the fossilized remains of their brains. The bones themselves don't preserve the brain tissue, of course, but their structure, particularly the size and shape of the fenestrae, or holes, offered valuable clues. Larger fenestrae, like those found in many hadrosaurs, the duck-billed dinosaurs, suggest a larger cranial cavity, potentially housing a bigger brain. This wasn't a simple linear correlation, though. The size and placement of the fenestrae were often linked to factors like muscle attachment, but the presence of these larger cavities indicated a potential for increased neural capacity. Similarly, the shape of the petrosal bone, a small, intricate bone tucked into the side of the skull, is proving to be a surprisingly sensitive indicator of cognitive evolution. Variations in the petrosal bone structure have been linked to increased processing abilities in some ceratopsian dinosaurs like Triceratops, suggesting a sophisticated auditory system capable of detecting subtle environmental cues. Beyond brain case analysis, paleontologists have turned to examining fossilized footprints and nesting sites. These sites provide tantalizing glimpses into social behaviors and problem-solving skills. The elaborate trackways left by herds of hadrosaurs, for instance, demonstrate coordinated movement and perhaps even communication, the ability to respond to each other's actions. The discovery of nesting sites, often containing fossilized eggs and juvenile dinosaur remains, presents an even more compelling argument. Some of these sites reveal evidence of parental care, with adults returning to and guarding their nests, suggesting a level of understanding and attachment previously thought impossible for dinosaurs. The arrangement of the nests, with some showing deliberate construction and protection from predators, implies a certain level of planning and awareness. Comparative studies with modern animals have played a vital role in interpreting dinosaur intelligence. Researchers often look to birds, the direct descendants of dinosaurs, for insights. Birds exhibit a remarkable range of cognitive abilities, from tool use and complex social structures in some species, to problem-solving skills in others. The intelligence of modern corvids, such as crows and ravens, is particularly relevant. These birds are renowned for their problem-solving skills, their ability to use tools, and their sophisticated communication abilities. Discoveries of fossilized dinosaur remains with evidence of tool use, such as a Deinonychus specimen with a stone embedded in its foot, potentially used to dislodge prey, further strengthen this connection. Furthermore, scientists are examining the sensory capabilities of dinosaurs, particularly their hearing and vision. The discovery of inner ear fossils in some dinosaurs suggests that they possessed a much more sensitive auditory system than previously thought, capable of detecting subtle sounds and navigating their environment with remarkable precision. Similarly, the structure of their eyes, combined with the understanding of their ecological niches, points towards enhanced visual acuity, potentially allowing them to spot prey or predators from long distances. The evidence suggests that certain dinosaur species were not simply seeing in a basic way. They were actively processing visual information, just as we do. The fossil of Nanotyrannus has been a particularly intriguing case. This small tyrannosaur, discovered in Utah, possessed a proportionally larger brain case compared to its body size, suggesting a higher cognitive capacity than its famous cousin, Tyrannosaurus rex. While Tyrannosaurus was undoubtedly a formidable predator, Nanotyrannus hints at the possibility of a smaller, more intelligent tyrannosaur, perhaps specializing in hunting smaller prey or engaging in more complex behaviors. It's important to acknowledge that assessing dinosaur intelligence is a challenging undertaking. We're interpreting the fossil record through the lens of modern animal behavior, which introduces a degree of subjectivity. However, the accumulating evidence, the detailed analysis of brain case morphology, the study of fossilized tracks and nests, and comparative research with birds, is painting a picture of a dinosaur world that was far more intellectually vibrant than we once imagined. The evolutionary path towards intelligence in dinosaurs wasn't a sudden leap, but a gradual process of adaptation and refinement, driven by ecological pressures and the inherent capacity for learning and problem-solving that existed within their lineage. As new fossils are unearthed and research techniques continue to advance, our understanding of dinosaur intelligence will undoubtedly continue to evolve, revealing even more fascinating details about these ancient creatures. The world of dinosaurs wasn't just one of towering giants and fearsome predators. Beneath the skin of these magnificent creatures, a surprisingly complex ecosystem thrived, an ecosystem of parasites. For a long time, paleontologists focused almost exclusively on the physical, the immense size, the sharp teeth, the powerful legs. But increasingly, we're realizing that dinosaurs, like all animals, were vulnerable to infection, and parasites played a significant, often overlooked, role in their lives. The fossil record offers tantalizing clues, slowly piecing together the story of these miniature tormentors. The discovery of fossilized parasites is a challenging endeavor. Unlike bone, which can be relatively durable and stand the test of time, many parasites are fragile, composed primarily of chitin, a tough, resilient material or soft tissues that readily decay. However, exceptional preservation conditions, often found in amber deposits or areas with specific mineral compositions, can sometimes yield remarkable insights. One of the earliest and most significant discoveries came from the fossilized stomach contents of various dinosaur species. Researchers have identified the remains of nematodes, roundworms, within the digestive tracts of hadrosaurs like Edmontosaurus and Parasaurolophus. These weren't simply accidental ingestions. The presence of numerous worm eggs and larval stages indicates that these dinosaurs regularly consumed parasitic worms. The nature of these parasites suggests a close relationship with the dinosaurs' diets. Hadrosaurs, with their constantly growing herds, would have been particularly susceptible to infection. The sheer volume of vegetation they consumed likely provided a constant supply of worms that thrived on decaying plant matter. Furthermore, the eggs of these parasites, often tiny and easily overlooked, would have been present in the fresh, moist vegetation. The presence of nematode eggs in dinosaur stomachs doesn't just tell us about infection. It also paints a picture of the dinosaurs' feeding habits and the ecological relationships within their environment. Beyond stomach contents, fossilized evidence has surfaced in other surprising places. In 2008, researchers unearthed what they believed to be the fossilized remains of a velociraptor infected with mites, tiny arachnids within its feathers. This discovery, made in Utah, is particularly intriguing. The mites were remarkably well preserved, encased in amber, and showed clear signs of feeding and burrowing within the dinosaur's plumage. This suggests that mites weren't just freeloaders, but had evolved a sophisticated relationship with their host, potentially benefiting from the warmth and protection provided by the dinosaur's feathers. The identification of these parasites isn't always straightforward. Paleontologists often rely on microscopic analysis of fossilized tissues, comparing them to modern parasites and understanding the evolutionary relationships between different groups. Furthermore, contextual information, the surrounding geological environment and the associated fossil assemblage, is crucial. For example, the discovery of fossilized nematode eggs alongside the remains of other dinosaurs suggests a shared environment and a complex web of interactions. Interestingly, the type of parasites found on dinosaurs varies depending on their size, diet, and habitat. Larger carnivores like Velociraptor tended to have a different parasite fauna compared to herbivores. This is likely due to differences in their diets and the types of environments they occupied. Smaller, more agile dinosaurs were probably more vulnerable to a wider range of parasites than larger, more heavily armored ones. The role of parasites in dinosaur health and mortality is a complex one. While some parasites likely cause significant morbidity, illness, and suffering, others may have played a more subtle role. It's plausible that some parasites could have weakened dinosaurs, making them more susceptible to predators or disease. However, it's also possible that certain parasites developed a mutually beneficial relationship with their hosts, perhaps aiding in digestion or providing protection against other pathogens. The exact nature of these interactions remains a subject of ongoing research. Furthermore, the presence of parasites can influence our understanding of dinosaur mortality rates. While large predators undoubtedly posed a significant threat, the contribution of parasitic infections to dinosaur deaths is increasingly being recognized. The fossil record frequently shows evidence of bone pathologies, abnormal bone growths and deformations, which could be caused by parasitic infections. These pathologies might have weakened bones, making dinosaurs more vulnerable to injury or collapse. Advances in technology, particularly in the field of paleoprotomics, the study of ancient proteins, are offering new ways to investigate dinosaur parasites. By analyzing the ancient proteins preserved in fossilized bones, researchers can potentially identify parasites even if the parasites' remains themselves are not preserved. This approach is particularly valuable for studying parasites that were exceptionally small or fragile. The study of dinosaur parasites isn't just about understanding the past. It also has implications for our understanding of evolution and the dynamics of ecological communities. It highlights the interconnectedness of life on Earth and the profound influence that microorganisms, including parasites, can have on the survival and evolution of large animals. As we continue to explore the fossil record and develop new analytical techniques, we can expect to uncover even more fascinating details about the lives of these magnificent creatures and the hidden world of parasites that shared their planet. The story of dinosaurs is constantly being rewritten, and each new discovery adds another layer of complexity to our understanding of their lives. A life, it turns out, that was just as vulnerable and fascinating as our own. The world of dinosaurs wasn't just a collection of individual creatures roaming a barren landscape. It was a bustling, incredibly complex system, a tapestry woven from the interactions between dinosaurs, their food sources, the plants they ate, the climate, and the very geology of the land. Understanding this requires a field of study called paleoecological reconstruction, essentially trying to build a picture of what a dinosaur's world looked and felt like, based on the evidence we find as fossils. It's a detective story, really, piecing together clues to recreate an ancient environment. The foundation of this reconstruction begins with fossil assemblages. These aren't just single dinosaur skeletons. They are collections of fossils found together in a specific location. A typical assemblage might include dinosaur bones, plant fossils, leaves, seeds, pollen, invertebrate fossils like ammonites and belemnites, which were squid-like creatures that lived in the oceans, footprints, and even fossilized dung coprolites. The key is that these fossils were deposited together, likely due to a catastrophic event such as a flood, volcanic eruption, or a sudden change in the landscape. Analyzing these assemblages allows scientists to deduce a great deal about the environment and the lifestyle of the dinosaurs that inhabited it. For example, consider the fossil site of Comeau Bluff in Wyoming. This site has yielded incredibly rich assemblages of hadrosaurs, duck-billed dinosaurs, alongside the remains of numerous carnivorous dinosaurs like Lithrinax. The abundance of hadrosaurs, combined with the presence of large predators, suggests a complex food web. It wasn't simply a case of the biggest predator always eating the biggest prey. There were likely multiple feeding strategies at play. Some hadrosaurs may have been opportunistic browsers, feeding on low-lying vegetation, while others, perhaps younger or weaker individuals, were targeted by the faster, more agile predators. The type of plant fossils found within an assemblage provides further insight. If a site contains a high proportion of fossilized fern spores, it suggests a warm, humid climate, much like parts of modern-day South America. Conversely, a predominance of fossilized cycad seeds indicates a drier, warmer environment, possibly similar to parts of Africa today. Analyzing the plant remains isn't just about determining the climate. It also reveals the types of food dinosaurs were consuming. Herbivores would have specialized teeth adapted to their specific diets: broad, flat teeth for grinding tough vegetation, or sharp, blade-like teeth for clipping leaves. Paleoecological reconstruction also relies heavily on geological data. The rock layers in which fossils are found tell a story of time and environmental change. Stratigraphy, the study of layered rocks, allows scientists to determine the relative ages of the fossils and to understand how the landscape evolved over millions of years. For instance, a site containing dinosaur footprints alongside fossilized river channels suggests that the area was once a floodplain, periodically submerged by seasonal flooding. The size and shape of the footprints can even indicate the behavior of the dinosaurs. Were they running in herds, or were they solitary hunters? Beyond the direct fossils, scientists use trace fossils, evidence of dinosaur activity that doesn't involve bones themselves, to paint an even richer picture. Fossilized footprints, trackways, and even fossilized nests provide invaluable information about dinosaur movement, social behavior, and parental care. The Laurasian dinosaur trackway at Tendaguru in Tanzania, for example, shows hundreds of footprints from various herbivore and carnivore species, suggesting complex social interactions and potentially even cooperative hunting strategies. Another crucial element is analyzing the sediment itself. The composition of the sediment, its grain size, its mineral content, can provide clues about the source of the water that deposited it, the energy of the depositional event, and the overall environment. Detailed analysis of sediment cores can even reveal ancient water temperatures and salinity levels, shedding light on the climate and hydrology of the dinosaurs' world. Furthermore, paleoecological reconstructions aren't just about understanding the dinosaurs themselves. They're about understanding the entire ecosystem, the intricate web of interactions between all living things. By combining data from fossils, geology, and sedimentology, scientists are increasingly able to recreate not just the physical environment, but also the behaviors, social structures, and ecological relationships of these magnificent creatures. It's important to remember that paleoecological reconstructions are rarely definitive. They are, at best, models, educated guesses based on the available evidence. As new fossils are discovered and new analytical techniques are developed, our understanding of dinosaur ecosystems will continue to evolve and refine. The more we learn, the closer we get to truly appreciating the astonishing complexity and beauty of the world these dinosaurs inhabited. It's a continuing journey of discovery, and each new find brings us closer to understanding these incredible animals in their proper context. If you're still awake and enjoyed this exploration of dinosaur facts, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Let the gentle echoes of ancient giants settle within you, allowing your thoughts to drift, calm and unhurried as the stars begin to whisper.